like ride the Eagles, or is he just saying run fast? Like, what's he saying?
I think he's just saying like get the hell out of here.
Or is he saying like ride the freaking Eagles because like you could do
They're
that?
in Moria. They're underground. They aren't in.
Okay.
Stop thinking of it.
All right.
But flying, like I guess.
Fly, you
getting up there.
All right.
Like don't wait for me. I'm like hoping. I'm sacrificing kind of like to give you guys time to don't waste that time watching me die.
Fair enough. All right. So graph is kind of tough to see on the screen on the pair deck, so it's up here for you. These are two velocity versus time graphs. Oops. One for object 1, one for object 2. Let's say these velocities are in meters per second. I don't know why they didn't put a unit on here. That seems silly to me. Okay, so that's object 1. This is object 2. And what you're supposed to do with that little drag thing is compare them based on displacement. Which one's got a greater displacement? Object 1 or object 2? Drag your shape to the appropriate box for that. All right. Where up in the heck?
Oh, yeah, I was calculating integrals there.
Kiana, cell phones or sweaty kids? Okay, put your cell phone away then. All right. And you can graph that as elasticity or All right, let's see how we're doing. We got 13 of 17 people responding. You're dragging the star to the graph that shows the greater displacement. Can't see the graph. There's the graph. And it is. Boop. Looks like most of the stars have been dragged to the top one. Okay, cool. So let me make some changes here to this. All right. So now drag the star to the correct thing. You're going to get annoyed with us over here, so I'm going to shift you over that way. Oh, wait. You're in here. I thought you were taking the quiz for physics. Sorry. Lo siento. I got too many people showing up weirdly. You want to take the quiz for regular physics?
Sure.
New student from where? From where?
Kentucky.
They let her in?
She just lived there for 2 months. She's from RC.
Oh, okay.
That's fair.
Fair enough. All right. So the stars are all over the place. They're not aligned, as it were. So, like, talk to your neighbor here quick. Which one's got the greater displacement? Drag your star there.
Oh, about the ones that like you drew?
Yeah. I redrew the graphs on the screen here, friends. Based on my redrawn graphs, which one's got the greater displacement?
Yeah, well, if he's asked, if he shows the different one.
All right. So now all but 3 people have dragged it down to the lower graph. We'll call that close enough for government work. So let's do. Oops. Let's go there. Let's go there. Yeah, okay, cool. I like that. All right, cool. Go with what you see now on the screen. On my screen on the front projection. All right, and it looks like most people are on the bottom one. And there's Blake. All right. Sure it was. He wouldn't do that. Yeah, he would. All right. How about if we go like this, and then like this, and this. All right. All right, go for it. No, I'm not.
You're having a
All right. Now, I'd like to say that people were able to quickly switch to the top one, but quickly is a relative term here, you 5.0ers. So what I want to know is, like, what is your shortcut that's allowing you to quickly, quotes, determine which one's got a greater displacement? What are you doing? Preference for the 1,000 most common words. 1,000 most common words. Not at the Blake family dinner table, but in general. Boop. Mr. Harding, whatever do you mean? I mean this, right? This is what you're doing. You add up the boxes and see where the extra ones are, okay? Graph with more squares under their lines is most moved. Add up the number of boxes filled below the line, okay? So that's kind of the idea here, right? So you're doing this thing that the Blake family calls calculus, but we in here call box counting, okay? This is finding displacement from velocity versus time graph. Okay? What do? Count boxes. All right? Now, there's something more that kind of goes in here and should be the first rule. Unfortunately, though, due to the Groundhog Day-like nature of my existence, I know this is the thing that's going to throw us for a loop later. First step should be find the area of one box, okay? So, like for me, I'm going to look at this one box, and I'm going to find the area of it, okay? So if we pull that one box out, what is the vertical dimension of it? See, I still haven't broken you. One what, bruh? 1 meter per second. And then the horizontal dimension? 1 second, okay? So the area of one box, we go base times height equals area. That was a lab some people had to do with some paragraphs. 1 second times 1 meter for every second. Cancel, cancel. 1 meter, okay? That's odd to say that the area of this box is 1 meter. It's not meter squared, it's 1 meter. And then I just box count. How many boxes? And then I'm there. Ooh, is it that simple? Let me complicate matters further by doing this. What? Yeah, but better. I'm going to do this action, kids. Whoa. And now my graph's going to look like. All right. So, drag your star to the one that's got the greater displacement here. Displacement. Which one's got the greater total displacement, if you will? Sure. Oh. Total? Like total? Are we talking practice?
Displacement is by definition.
Displacement.
Displacement is the total distance from the endpoint.
Change of position, bro. Change of position. All right. Let me. Sorry, I should have drawn it this way. Let me draw it this way. All right, there you go, bro. Where's your star? it looks like most of the stars have gone south for the winter. So let's check into that. We could, because we're west high, best high, we could solve this as a math way. And we could go 1 meter per second times 3 seconds plus -1 meter per second times 3 seconds. That's going to equal 3 meters plus -3 meters. That's going to equal 0. Okay? Or can I solve this with box counting? Go back to your rule here, friends. And do you need to make some revisions to your rule to account for the present situation? What do you need to be understanding in a scenario like this? So pair deck. What? It's locked? Dang it. I forgot the keys. All right, there you go. Suri. At least make it seem like it was somewhat challenging on the Jeepers. How am I supposed to feel about it? Oh, Blake. Hang in there, Gelbach. All right. So friends are saying things like count all the boxes, add up the boxes. Boxes under the x-axis are negative. Add boxes above 0 and subtract boxes below 0. Number of boxes above the x-axis minus the number of boxes below. So we're kind of wordy with like the above and below. Like which box is above, which box is below. Here's the problem we'll run into. Okay? So help your neighbor help themselves. This is the ghost of physics future. They're going to count these boxes as well as these boxes. Okay? So is there a word that we can use that allows us to ditch above and below and focuses on the boxes we really need? Which boxes do we need? We need the boxes that are what? Run that by your neighbor really quick and then throw it into the pair deckage. Is there something you can say in one clause that is more efficient than the two clauses of above, comma, and below? We want the boxes that are because right now I'm saying these boxes are the boxes that are below the line. But that's not correct. Let's adjust this. We need to say what? The boxes that are what? That's what I'm asking you to run by your neighbor real quick. Man, I'm out of minutes. Oh. All right, here's the friends that are smelling what I'm stepping in. Count the boxes between the line drawn and the x-axis. We want the boxes that are between the x-axis and the curve. It's not really a curve here, but you know what I mean. Box between the line drawn and the 0 on the x-axis, okay? So the x-axis is the blue line. There we go, right? Here's the x-axis. So I don't want any of this business down here. I only want the ones that are between the velocity time graph and the x-axis. Okay, so then I would also similarly pay attention to these boxes because they are between the line and the x-axis. Okay, so as far as our rule set, we're finding displacement from velocity time. We're counting boxes, and I should add to that between the velocity, or how should we say there? Counting the boxes between the graph and the x-axis. What's a better way to state that? Between the line and the x-axis, between the curve and the x-axis. Graph of velocity and the x-axis. Boxes above x-axis are positive. Boxes below x-axis are negative. But again, the thing that's going to throw people off more than anything, it should be rule 0. First, find the value and unit of one box. Okay? Do that, and you're going to have a much harder time screwing it up. Skip it like everybody and their mother does the first 3/3 of the year, and it's going to be problematic. Okay? So find the value in the unit of one box before you do any box counting. All right. So let's try this out then. I'm going to give you this graph, and you're going to determine the change in position, which is the what? Displacement. Okay. From t equals 3 hours to t equals 5 hours. Okay. So find that and put it into the pair deckage. Some of you are confusing me for a person that would accept an answer without units. Correct units would be good. Hang in, Calvin. All right, here are some of the various answers that I'm seeing. Negative 80 miles, 0 meters, negative 80 miles, 80 miles, 80 miles, negative 80 miles. So talk to your neighbor about units, okay? And how you're arriving at your answer from 3 to 5. I don't know why I turned that on. I don't want to talk over it. All right. So I don't think I did a good enough job shouting at the other classes about this, but since I put it in all caps over here, you did it, because most other hours it was kind of 50-50 between getting answers of -80 or -160, right? Find the value and unit of one box. Oh, yeah. So if we find the area of this one box here, how tall is that one box? That a kids. 20 miles per hour. And how wide is this one box? That a kids. Okay. So this is 20 miles per hour multiplied by 0.5 hours. Boop, boop. 10 miles per box. Now we go over here and count boxes. -1, -2, -3, -4, -5, -6, -7, -8. You got -8 boxes times 10 miles per box. You're going to get -80 miles here. Boxes cancels out, okay? Or you could just treat it like one really big box and do this thing called the calculus to get the area of this rectangle, okay? This side of the rectangle is -40 miles per hour. This side of the rectangle is 2 hours. You go -40 miles per hour, and you do that for 2 hours. Clearly, you're going to go -80 miles, okay? That's what up with that. So, it's in your head. All right, so part B, determine the change in position from time equals 5 to time equals 5.5 hours, okay? See if we can get 100% on this one. Nope, we cannot.
I thought that was a whole box.
What up? Displacement, yes. Displacement is fancy, so you would take into account negatives.
Oh, yeah, I can see those numbers.
I didn't. I thought it was a whole box.
Yeah, right. I understand that.
It's confusing. It could be.
Hey, do you prefer MI or MILES?
I prefer meters and kilometers, but if pressed, I'd go MI for miles. But then still love me when I say MPH and mean miles per hour.
How do I do with the buggy line?
What?
That is silly. It's crazy. It is.
What?
Yo, Brady.
Yo, Brady.
Come on.
Hey.
Yeah. Oh, yeah. Shoot the one with the one-pair glasses.
That can never come back to haunt me, right? That's just some random kid in the hallway.
It's your son.
All right.
Do the electric thing on him.
No. All right. How'd we do? 15 miles, 15 miles, 15 miles, 15 miles, 15 miles, 30 miles, 15 miles, 15 miles, 15. 50 miles, 50 miles, 50 miles, 15 miles, 15 miles, 15 miles. Okay, cool. Somebody's losing a half point for units, and somebody's off by a factor of 2. But yeah, what do you got here? You got 30 miles tall, 30 miles per hour tall by half an hour wide. You're going to get 15 miles there. Okay? Coolio. All right. So do me a solid. Construct a quantitative position versus time graph for this motion. It does say here to assume a position of 5 miles at time equals 0. Plus C, bro. Plus C, bro. Plus C, bro. Okay. So based on that velocity versus time graph, you draw the position versus time graph. Okay, I've had it. Don't care about it. You have the sheet? I have the sheet. You have the sheet of this? No. Okay. So what
Why can't we do it on here then?
there's this thing called pick it up when you come into the room, you savages. Jeepers.
There's this thing called like simple.
What? Whoa! Sign that kid up for the ultimate frisbee team if you still have one.
Yeah, wait. Not four.
Yeah.
There's an only
Girlfriend.
-5. For what motion? Oh, this one.
Oh, for the motion.
Wait.
Oh yeah, because it's Boston. 4 miles an hour. Oh yeah.
Oh, wait.
Yeah.
Hey, over there in the pair deck then too, I'm looking for your final position. Once you've got your graph, yeah. Plus C, bro.
Like, do you like teach calculus?
I just did, dude.
Like,
I
do you,
just
like, actually
did.
do it?
I just did.
Officially?
I just did.
I know you just did.
Yep.
I would agree that he has a superior teaching ability. Would you not know? How can someone be so privileged in society?
Oh, sorry. I didn't have the pair deck question up for you. There you go. So in the pair deck, once you got your graph drawn, I want you to think about what is the final position for the outcome. All right. What you got? What you got? What you got? Again, on the pear deck, you're throwing in your final position. Not asking you the change of position. I'm asking you your final position. Oh, yeah. Final position. Not the displacement. Oh, we didn't talk about that yet. Blake asked me about directions of rotation at some point in this unit. Yeah. That'll help us make sense of the tip of this stylus, which is left-hand thread. That means righty loosey, lefty tighty. All right. All right, friends, where are we at with this? We've got negative 15 miles, 0, negative 15 miles, negative 20 miles, negative 15 miles, negative 15 miles. So I'm going to number the axes like this. Okay. And it's got to start at 5 because it tells me it starts at 5. The change in position in this first chunk is going to be, boop. Oh, man, come on. Where's the button? So this first chunk is 30 miles. We already talked about this chunk is negative 80 miles. And this chunk on the back end is another 30 miles. Okay? So starting from 5, I'm going to have a change of position at 30 miles by time 1.5 hours. That's going to put me at 35. Then I don't change position at all. My velocity is 0 from 1.5 to 3. If my velocity is 0, I'm not changing position. If my velocity is 0, I'm not going anywhere. Then I got to change a position of negative 80 miles. I'm at 35. Hey, friends. Here's how change works. I go initial plus change equals final. My initial position is 35 miles. Okay, I'm saying initial as of this point. The change is going to be negative 80. So then my final is going to end up being negative 45 miles. So in this window of time, between 3 and 5, I've got to end up at negative 45. So it's a little bit below the graph there. Like that. And then my final change of position, I'm at negative 45. My change is going to be 30. So my final position ends up being negative 15. There we go. Negative 15 miles. Thank you, sir. Not if I'm going to harangue you guys for it. All right. So draw a motion map. Nah, I don't think so. I don't feel like it. So this is in the notebook. You can go back and look at this stuff. This video gets posted on YouTube. You can go back and review it later if you have questions on what we're doing here. But I want you to try to apply it to this thing, which you don't have because I need to hand it out to you. This is my favorite type of problem. It's called a practice the model problem, which is a way more fun thing to do when we have models plural. Right now we have 1. So it's going to be pretty straightforward because all you have to do here is figure out to which of the following 3 problems does the constant velocity particle model apply, and then you only have to solve the one or ones to which the constant velocity particle model applies, because we don't know any other models yet. Okay? Once you identify where the CVPM is applicable, you're going to need to draw at least 3 diagrams and or graphs that illustrate the situation. Guess what? You only know 3 diagrams and or graphs. Motion map, position versus time graph, velocity versus time graph. Okay? Yeah, you gotta meet every student at their level, right? I gotta provide you with an adequate challenge.
Oh, nice.
Oh, wow. That's so Iowa State. So this is a really, really important skill. Hey friends, this is probably like one of the most important skills at the end of the year is being able to identify which models apply. Like when you're taking the AP exam, there are going to be 3 free response questions, and they're going to probably have been priced. I think there are 13 units of study to that point. So 3 questions, 13 units of study. Each FRQ is going to involve a little bit of this, a little bit of that. You need to be able to know which words key you in on. Ooh, this part is CBPM. Ooh, this part is this other model. Okay? So that's why we're doing this right now. So explain your reasons for your answers here as to why the CBPM does or does not apply. What are the key words or terms that you're kind of like zeroing in on that tell you, ooh, not CBPM or CBPM, okay? And then again, once you've done that, draw your at least 3 diagrams and or graphs, and then get quantitative with it. Use the tools from the model to solve for any unknown quantities, okay, that show up in those graphs and or diagrams. I don't know what step D is really talking about. We probably will skip that. But, yeah. Blake, question?
Oh, really important. Why is the A in apply capitalized?
Why is the who, the what?
The A in the word apply at the top capitalized.
A and apply at the top. I do not know. I'll take it up with whomever I stole this from. I get my stuff from a place called Teachers Don't Pay Teachers, aka Twitter.